Excuse me. Great, thank you. And good to see everyone here once again in person. Indeed, I'll be talking about the sharpening the distance conjecture. This talk will be based primarily on a paper from last June with Muldrow, Ben, Sami, and Yue. A paper I wrote in August last year, as well as some work to appear with Muldrow, Ben, Jacob, Ignacio, and Irene. So a quick. Oh, this is inexplicably ceased to work. There we go. Okay. So a quick outline. I'm going to start off by proposing a sharpened version of the distance conjecture and providing several lines of evidence for this sharpened distance conjecture. And then we'll look at some of the implications of it. So first of all, the distance conjecture says, first of all, massless scalar fields parameterize moduli space of vacua. And then the claim is that in large distances in moduli space, a tower of particles becomes exponentially light with increasing field distance. So as the VEV of some scalar field phi goes to infinity, the mass scale associated with this tower decays exponentially. And here in this talk, we're going to be most interested in this parameter lambda. It's long been believed. This has inexplicably stopped working again. Is there a button I can press or? It's working now. Okay, great, thanks. So it's long been understood that this coefficient lambda, which appears in the distance conjecture, must be order 1 in Planck units. This goes all the way back to the original paper by Oguri and Vafa. But the precise set of values that are allowed for lambda has been a subject of much discussion and debate. So the main point of this talk and of our associated paper is to propose a lower bound on lambda. For the lightest tower in a given infinite distance limit, lambda is bounded below by 1 over the square root of d minus 2. Note that a typical infinite distance limit will usually have multiple towers with different values of lambda. The claim here is that there's always at least one, which will be the lightest tower, which satisfies this bound, even though other towers might be heavier and might not satisfy this bound. And throughout this talk, when we say, I'll refer to this as the sharpened distance conjecture. The claim that not only is the distance conjecture satisfied, but that it's satisfied with a coefficient that satisfies this bound. Now, before we get to this, it'll be useful for us to talk a bit about the emergent string conjecture, because that will play an important role in what follows. The emergent string conjecture of Lee, Lerche, and Huygens holds that any infinite distance limit in moduli space is either a decompactification limit or an emergent string limit, which will be accompanied by towers of Kaluza-Klein modes and string oscillator modes, respectively. It's not quite right to say that the sharpened distance conjecture implies the emergent string conjecture or vice versa. But when they're put together, a very simple and consistent picture of infinite distance limits in moduli space emerges. So with this, let's talk about some evidence of the sharpened distance conjecture. I'll sketch a few lines of evidence in this talk, and the first one is dimensional reduction. So it's this observed fact that many of the most well-supported swampland conjectures are exactly preserved under dimensional reduction. The weak gravity conjecture is a great example of this. It has this order 1 coefficient gamma, and gamma, the correct value of gamma, has this nice property that it's exactly equal under dimensional reduction. Turning this logic around, if you didn't know what the correct value of gamma was for the weak gravity conjecture, you could actually deduce what it is simply by demanding that it should be preserved under dimensional reduction. And so you might be tempted to try the same thing in the case of the distance conjecture. So to this end, suppose we start with a tower which satisfies the distance conjecture in capital D dimensions in the limit as the dilaton phi goes to infinity. Here, lambda sub big D is an order 1 number that we want to determine. After reducing on a circle, this tower of particles will gain some dependence on the radion. And if we redefine a new scalar field to be this linear combination, canonically normalize it, we find a relationship between lambda sub big D and lambda sub little d. This relationship is solved by setting lambda equals 1 over square root of d minus 2. Big D for big D, little d for little d. So the lesson, although it's hard to read, is that lambda sub d equals 1 over square root of d minus 2 is exactly preserved under dimensional reduction. This is our first hint that there's something special about this particular value. And more evidence comes once we include Kaluza-Klein modes into the story. When we compactify this theory on a circle, we get not only the tower that comes from the higher dimensional tower, but we'll also get towers of Kaluza-Klein modes, which scale with the radion like so. The Kaluza-Klein modes of the graviton don't depend on the dilaton, but they scale with the radion with this square root of d minus 1 over d minus 2 coefficient. It's helpful in visualizing this setup to define these scalar charge to mass vectors zeta sub I, which is given by the negative of the logarithmic derivative of the mass with respect to the ith scalar field. So you can see that for the Kaluza-Klein modes, they don't depend on the dilaton, so we have a 0. But then they scale with the radion with this square root of d minus 1 over d minus 2. Hence, we have this value here. And if we suppose that the higher dimensional theory saturates the sharpened distance conjecture, then we'll have a tower of particles, which reduces to this tower of particles right here. So how is one supposed to read this plot here? Well, the fact that the convex hull of these 2 points lies outside of this ball of radius 1 over square root of d minus 2, at least in these directions, is telling us that the sharpened distance conjecture is satisfied in these directions in the dilaton-radion plane. So for instance, if you were to take the radion to infinity at fixed phi, that's going off to infinity in the y direction of this plot. Lambda here, the lambda of the lightest tower, comes from the Kaluza-Klein modes. It's given by square root of d minus 1 over d minus 2. If you go off to infinity in this direction here, the lightest tower will be these particles here, with lambda equals to 1 over square root of d minus 2. And if you go off to infinity in any intermediate direction between here and here, you find that the sharpened distance conjecture is satisfied with lambda strictly greater than 1 over square root of d minus 2. So the sharpened distance conjecture is satisfied, at least in these directions, by the tower of Kaluza-Klein modes, assuming that the sharpened distance conjecture is satisfied in the higher dimensional theory. Now you might ask, what about the case where we take the radion or the dilaton to negative infinity? In that case, in order to satisfy the sharpened distance conjecture, we need for the convex hull of the scalar charged mass vectors to contain this ball, which means that we need some additional towers. And in practice, these additional towers in string theory come from winding modes. So as a twin model, suppose that we have in capital D dimensions some string which becomes tensionless in the phi goes to infinity limit, and whose string oscillator modes saturate the sharpened distance conjecture. If we compactify this theory on a circle, we find Kaluza-Klein modes, string oscillator modes, and also winding modes. And here we assume that there's an S-dual version of the string, so that the figures here are left-right symmetric. And you can see that together, the Kaluza-Klein modes, the winding modes, and the S-dual winding modes together satisfy this convex hull condition. The convex hull of the scalar charged mass vectors contains this ball, which means that the sharpened distance conjecture is satisfied in every direction in the dilaton-radion plane. In fact, we learned something else that's very important and very interesting from these plots. You notice that there are a number of points of tangency, here, 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 where the convex hull meets this ball. These correspond to the limits where the sharpened distance conjecture is saturated. Lambda is exactly equal to 1 over square root of d minus 2. And what's interesting is that we see here that these are precisely the emergent string limits, because they all feature towers of string oscillator modes. And remarkably, this is even true in 5 dimensions, where we have this additional accidental point of tangency, but we also have the string oscillator modes for the magnetic monopole string. So putting this together with the emergent string conjecture, we have a very simple picture. The sharpened distance conjecture should be saturated precisely in the emergent string limits, and it should be satisfied with room to spare in the decompactification limits. So this is what we expect from dimensional reduction. A similar analysis could be done not just for compactifying on a circle, but on a more general n-dimensional manifold. But now let's talk a little bit about some top-down evidence, examples where this actually happens in string theory. And the simplest case we can consider are just the 10-dimensional string theories that we know and love. All of these theories have a dilaton which by convention we'll take to go to infinity in the weak coupling limit. The tension of the string scales then with the canonically normalized dilaton, like so, which means that there's a tower of string oscillator modes whose mass goes like the string scale, which goes like the square root of the tension, which precisely saturates this bound. So indeed, once again, the emergent string limit saturates the bound. S-duality gives us the same thing in the strong coupling limit for these theories. And the remaining string theories, the strong coupling limits, are decompactification limits to 11-dimensional M theory. We get this famous square root of d minus 1 over d minus 2 scaling, and the sharp and distance conjecture is satisfied comfortably. So once again, emergent string limits saturate the bound, decompactification limits satisfy it with room to spare. If we take, say, type 2b or type 2a string theory and reduce it on a circle, we find precisely the scenario we studied before. Oops. Where we have this string theory, we have the S-dual string theory, and together the winding modes, the Kaluza-Klein modes, and the winding modes of the D string satisfy the convex hull condition, and the sharp and distance conjecture is satisfied. There's another plot that's similar to this one that one could draw to illustrate this scenario. Here, I'm not plotting the convex hull of the scalar charge to mass vectors, but rather I'm plotting as a function of angle in the dilaton radion plane, the largest lambda value. That's what the blue curve is showing here. So for instance, if you were to take the radion to infinity with fixed dilaton, again, we have these Kaluza-Klein modes, and these will be the lightest tower everywhere along here until we get to the emergent string limit. And along this infinite distance limit, if you imagine going out to infinity in this direction, the lightest tower are these F string oscillator modes, and here they're the D string oscillator modes. Again, you can see that the sharp and distance conjecture is satisfied. It's saturated precisely in these two emergent string limits. And you can also see here how the different regions in the dilaton radion plane correspond to the weak coupling limits of the different theories. So here, the theory is described by 2b, here it's type 2a, here it admits an M theory description. This plot will be important for us in a few minutes. But anyway, continuing with type 2b, if we keep reducing it on a circle down from 9 to 8, 7, 6, 5, 4 dimensions, we find in all cases, after significant effort by the UMass Amherst contingent of the collaboration, that this bound is indeed satisfied in all cases and saturated in certain limits. And once again, of the limits that we have checked, the ones where it's saturated are precisely the emergent string limits. So this, of course, is all maximal supergravity. You could ask, what about if we consider theories with less supersymmetry? As usual, things get more difficult. But in forthcoming work, we're looking at the case of 9-dimensional heterotic string theory. So heterotic string theory on a circle. This case is a little bit subtle, because naively, you might suspect that the convex hull should look something like this, where we have the type 1 winding modes of the type 1 string that's dual to the heterotic string, S dual to the heterotic string. But then because the SO32 heterotic string is self-T-dual, if we don't turn on any Wilson lines, these type 1 winding modes will be reflected by T-duality, give us a point here. The problem is that this figure is incompatible with the known fact that this limit should be an emergent string limit, which means that this line segment here should actually be tangent to the point here. So the second try, this is wrong. A second naive try, you might suspect, is that the convex hull should look a little bit like this. The problem with this is that, first of all, we're just ignoring the type 1 winding modes, but also we have this mysterious point here, and it's very unclear where such a point would come from. It turns out that the right answer here is to note something that's different about the heterotic case than the type 2 case, which is that not all of these states are BPS. In particular, the type 1 winding modes are non-BPS states. And that means that this point here can slide around along this line segment depending on where you are in moduli space. And so this is indeed what happens. And as a result, if we plot this largest lambda as a function of the direction in moduli space, the curve ends up looking a little bit something like this. When you're above this line here, when you're in this region here, the type 1 winding modes will be down here. If you were to move in moduli space, you cross this line here, then the type 1 winding modes will slide up to here. And when you look at things carefully and you study how lambda varies, the lightest tower, the lambda of the lightest tower varies as a function of which direction you're going off in moduli space, you find this blue curve here. And indeed, this blue curve contains this ball, meaning that the sharpened distance conjecture is satisfied. Again, it meets the ball at 3 points where the sharpened distance conjecture is saturated, and these are precisely the emergent string limits, 1 heterotic, 2 type 1. Yeah, right. So that's what good question. So this is not the convex hull of the scalar charge to mass vectors. That, of course, is convex. This is looking at some infinite distance limit, and you ask what's the lightest lambda. And that does not need to be convex, as we saw in the type 2b case, as we see here. Yeah. Thanks. So there's also an important lesson that's to be learned here, especially in thinking about the emergent string conjecture. So as noted by these authors back in 2007, and as seen in our analysis, decompactification of type 1 prime string theory in 9 dimensions leads to a running solution. In other words, the string coupling runs as a function of position. This means that we don't have a counterexample to the emergent string conjecture per se, but there's an important caveat to the emergent string conjecture, which is that not every decompactification limit leads to a higher dimensional vacuum. Here, we don't get a vacuum, we get a running solution. So the emergent string conjecture, properly understood, should therefore say that every infinite distance limit either gives an emergent string limit or a decompactification limit, which may or may not lead to a higher dimensional vacuum. Anyway, we can do a similar analysis for E8 times E8 heterotic string theory. We find this plot here, looking at lambda. Again, the sharpened distance conjecture is satisfied. There's 1 point of tangency, or not tangency, I guess, 1 point where this curve intersects the ball, which is the emergent string limit, the E8 times E8 heterotic string. And here, you'll note that the hull, this blue curve, strictly contains these points here. It doesn't intersect them, which means in a sense that the type 1 prime emergent string limits here are obstructed. One can't actually reach the type 1 prime emergent string because you have lighter towers, which are controlling the relevant physics in this infinite distance limit. So every direction here, except for 1, is actually a decompactification limit. So this is the top-down evidence I wanted to discuss. Finally, let me talk a bit about some bottom-up evidence from minimal supergravity. And here, I need to make one other quick aside to tell you about some other swampland conjectures. The tower weak gravity conjecture, which has, I think, been discussed at some length in this program so far, says that anytime some gauge coupling G vanishes in, say, some infinite distance limit, there should be a tower of particles which become light at the energy scale G in Planck units. Similarly, the weak gravity conjecture applied to two-form gauge fields tells us that there should be a string whose tension vanishes linearly with G, which means that the tower of string oscillator modes associated with the string will have a mass that goes like the square root of the tension and therefore like the square root of G. These are important because that means that if a gauge coupling or a two-form gauge coupling goes to 0 in some infinite distance limit, then if we know how the gauge coupling scales with distance, we can read off how the masses of these towers will scale as well. So let's do this for the case of 5-dimensional supergravity. Minimal supergravity, 5 dimensions. Quite simple compared to many other theories because the structure of the theory is controlled largely by this cubic function, the pre-potential. It's a cubic function of these homogeneous coordinates, which are identified under simultaneous rescaling. And what we're going to do in this talk is to consider a straight line path in the space of these homogeneous coordinates. So we take all the yi's to be linear functions of some parameter s. And we'll assume now that the limit as s goes to 0 lies at infinite distance in moduli space. It's not too hard to show that if s equals 0 is an infinite distance, then the pre-potential must vanish in the space of these homogeneous coordinates at s equals 0, and it must vanish either linearly or quadratically because of this assumed straight line form. So these are two cases, and we'll assume, first of all, we'll consider the first case, where the pre-potential vanishes linearly with S. One can then work out how the gauge couplings, smallest gauge coupling and largest gauge coupling, scale with geodesic distance, rho. So rho goes to infinity here, corresponds to S goes to 0. And we find that the smallest gauge coupling scales with this coefficient. The largest gauge coupling diverges with this coefficient. This means that if we apply the tower weak gravity conjecture to this gauge field, we get a tower of particles whose masses are bounded above by this square root of d minus 1 over d minus 2 coefficient. And if we apply the weak gravity conjecture for strings to the 2 form, which is dual to this 1 form, in 5 dimensions, 1 forms and 2 forms are dual, then we get a tower of string oscillator modes, which are bounded above with this coefficient here. And if you look at these coefficients for a few minutes, you'll realize that they look very familiar. This is precisely the coefficient that we had for the dimensional reduction from one higher dimension, where we looked at the tower of the Kaluza-Klein modes. And this is precisely the scaling coefficient that we had for the tower of string oscillator modes after reduction. So in other words, this is precisely the scaling that we expect for decompactification from 5 dimensions to 6 dimensions. A similar game can be played for the second case, and you might even be able to guess what we're going to find. In this case, where pre-potential vanishes quadratically, we find precisely the 1 over square root of d minus 2 scaling for both this one and this one, which is precisely the scaling that we had for the emergent string limit when we studied the dimensional reduction. Now, the reason why this is also remarkable is that we haven't assumed any UV input here other than simply the tower weak gravity conjecture and the weak gravity conjecture for strings. Other than that, there was no assumption about string theory. All we looked at was the massless content of 5-dimensional supergravity. And just from the massless spectrum, from the form of the prepotential and the gauge couplings and how they depend on the prepotential, just from that, we read off precisely the scaling behavior that we expect for the sharpened distance conjecture to be satisfied, for it to be saturated precisely in the emergent string limits, and everything is also consistent with the emergent string conjecture. And it turns out that this is true not only in 5-dimensional supergravity, but also in 6, 7, 8, 9, and 10-dimensional supergravity as well. In all cases, we can study how the gauge couplings and the 2-form gauge couplings scale with distance in infinite distance limits. We find in all of these cases that we get either this 1 over square root of d minus 2 scaling, or we get the square root of d minus 1 over d minus 2 for the Kaluza-Klein modes, and the 1 over square root of d minus 1 times d minus 2 for the string oscillator modes, or some intermediate regime between the two, which would correspond on this plot to not this point here or this point here, but some direction in between them. So all of this fits perfectly, as I say, with the sharpened distance conjecture. We always have at least one tower with a lambda, which is greater than or equal to 1 over square root of d minus 2. And all of this fits perfectly with the emergent string conjecture. And again, the only UV input here is simply the weak gravity conjecture. Everything else follows simply from the supergravity. So hopefully you're now all convinced from the dimensional reduction analysis, the d equals 4, not yet studied. So far, our work is focused on 5 dimensions or higher, with the exception of, we did look at the at type 2 string theory, so maximal supergravity compactified to 4 dimensions. And there we found that it was satisfied as well. But 4 dimensions is the next case to consider. Yeah. Okay, so hopefully you're convinced. We've seen this evidence from dimensional reduction. We've seen evidence from compactifications of string theory and M theory. We've seen evidence from minimal supergravity, and all of them really point and tell the same story, that the sharpened distance conjecture is saturated in emergent string limits, satisfied with room to spare in decompactification limits. Now let's talk a little bit about the implications of this conjecture. And I want to start with the implications for asymptotic scalar field potentials. So scalar field potentials in quantum gravity have this property that, at least in the cases we can look at in the string landscape, they seem to fall off exponentially with proper field distance, where c here is some order 1 coefficient, which again, we want to fix. This bound suggests a bound on the gradients of the potential in asymptotic regimes of scalar field space. And I want to strongly emphasize the asymptotic regimes. The argument I'm going to make today really just applies in these regimes where the distance conjecture can be applied. So we expect that there will be a bound of this form in asymptotic regimes. And the goal here is to determine C. So we can do this, actually, by relating this to the work we've done already under a couple of additional assumptions. So we're going to assume, first of all, that the sharpened distance conjecture applies beyond massless moduli to scalar fields with potentials. This is something that goes back, again, to the original work by Oguri and Baffa. It's been argued for by Baume and Palte and others as well, but it is an assumption we're going to make. We're also going to assume that the emergent string conjecture is true, which means that not only is this bound satisfied, but it's satisfied either by Kaluza-Klein modes or string oscillator modes. With these assumptions, we can conclude from the second one that the string scale or the Kaluza-Klein scale is going to be bounded above as phi goes to infinity by this decaying exponential here. And if we assume that the potential falls off with this coefficient C, then as long as C isn't too large, which is the case that we're interested in, the Hubble scale will go like the square root of V. And if we therefore then require that H is less than the string scale and the Kaluza-Klein scale, we finally arrive at C greater than or equal to 2 over the square root of D minus 2. You might wonder where this bound is coming from. If the Hubble scale is not smaller than the string scale, then we don't have an effective field theory description at all. We're entering into a stringy phase because the tower, we have a whole tower of string modes that are lighter than the Hubble scale. If the Hubble scale is not smaller than the Kaluza-Klein scale, then it means that the horizon size is actually smaller than the radius of the extra dimensions. So in that case, we really don't have a d-dimensional cosmology, we have a decompactification. So we're assuming here that we have a d-dimensional cosmology that's governed by effective field theory. And that's what leads to this bound here and to this conclusion. And this bound here is actually quite familiar. It is, first of all, equivalent to the strong energy condition in these asymptotic limits of scalar field space. It's also precisely the condition you need to forbid accelerated expansion of the universe in these limits. It's exactly preserved under dimensional reduction, just as the lambda equals 1 over square root of d minus 2 that we saw today was. It's satisfied in all infinite distance limits with a supersymmetric vacuum. And at least in my view, it likely points us to the fact that quintessence, like de Sitter space, is at best metastable. It's widely believed that in the string landscape, de Sitter vacua, if they exist, are at best metastable. We may be living in de Sitter space, but eventually we're going to decay to a Minkowski vacuum or an ADS vacuum. What this result seems to suggest is that you can't just sit out here asymptotically far on the potential and slowly roll and have accelerated expansion that just lasts indefinitely. You quite possibly can have accelerated expansion. After all, we're living in a world with accelerated expansion. But the point is that that can't go on indefinitely. It'll last only a finite period of time. That's very much consistent with this result here. Finally, we can apply roughly the argument we just made to 4 dimensions. And if we make a couple of additional assumptions, this can have important consequences for large field inflation. So we're going to make the same assumptions we just did, but with one other. We're going to assume that the string scale or the Kaluza-Klein scale is bounded above by this exponential. But then we're also going to put in the Planck scale here. And this is important because nothing I've said so far would lead you necessarily to put it in the Planck scale as opposed to 10 times the Planck scale or 1,000 times the Planck scale. Obviously, the Planck scale is a very natural scale for quantum gravity. So this seems like a natural thing to do, but it's important that it's an important caveat to note. So we're putting in the Planck scale here, multiplying this exponential. We'll assume that we have a large field model of inflation. So the Hubble scale is about 10 to the minus 4 in Planck units. And if we therefore restrict this to be smaller than this scale here, this tells us that phi cannot roll a distance larger than about 14 m Planck. And this is actually an interesting bound on inflationary models. It tells us, for instance, that m squared phi squared inflation is in the swampland. And more generally, it leaves very little room for the required hierarchy of scales, that the Hubble scale is supposed to be much less than the Kaluza-Klein scale. which is supposed to be much less than the string scale for parametric control in stringy inflation. One thing to note is that we're using here this is the displacement of the field. So it's less clear that this applies to models like axion monodromy, where we might have a large distance, but perhaps not a large displacement. More work is needed. So thanks to the amount of time, let me finally summarize. The main thing to remember, if you remember nothing else from this talk, the distance conjecture parameter is bounded below by 1 over the square root of d minus 2, and saturation occurs precisely in the emergent string limits. We've seen a number of independent lines of evidence for this bound from dimensional reduction, examples from string theory and supergravity, and the connection to the emergent string conjecture. The bound may have important consequences for large field inflation, scalar field potentials. Notably, it rules out accelerated cosmological expansion and squared phi squared inflation. And we've also seen an interesting caveat to the emergent string conjecture. The decompactification limits don't necessarily lead to higher dimensional vacuums. Thank you.
Very nice about them. I'm not going to understand why you say string emergent conjecture does not use. It seems like it did.
Right. So, well, it's closely related, but I think in the original formulation of the emergent string conjecture, there isn't necessarily the statement that lambda is equal to 1 over square root of d minus 2 in the emergent string limits. I agree. Okay, sure. Yeah, I mean, I think I would say the emergent string conjecture plus a calculation, which you of course would call trivial, but for the rest of us is maybe a little more difficult. Right. I mean, I think it's clear in the simple cases of 10-dimensional string theory, 9-dimensional string theory that this will be the case. I guess it's maybe not so totally obvious that any string. Right.
And you will get the property of the Einstein mathematically of the identification to be open string. So all the examples that we have checked is consistent with that. But sometimes you just start with the field of action, and you have a sequence.
Yeah. Okay, sure. Thank you.
In this model, example that I have of Supergravity, what do you know on the emergent string? How many times I can put it? I didn't quite check that, but in the Supergravity number.
Okay, yeah. So I mean, in the supergravity analysis, all we're looking at is the gauge couplings for the two-form gauge fields, and we're assuming that there's some string. We're also, I guess, assuming that this string is fundamental in the sense that it has a tower of string oscillator modes, as opposed to some EFT string or something. It did go into the analysis, right? I guess, yeah, that would be an interesting thing to check. But yeah, we have not checked that. Good point.
So I want to talk about this case where you take artifacts to the linear level. So that case where you currently combine this with dimensional massive vector, which of course have a lower spiral, right? So I want to ask you, do you think in all the cases where you're not going to with lower character, I'm holding say the way or will it be themselves?
Yeah, that's a really good question. I don't think I have a great intuition. I guess it wouldn't surprise me, but this brings up a point I wanted to say that I think this fact that we can get the running dilaton, I think that's an important point, and it means that it's worth going out in the landscape and looking for other examples where this happens, and whether or not those will all correspond to the case you mentioned is not so clear to me as of yet.
So let's back to again.